Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always it is an honor and a privilege to be serving you here today as it is every day here in my virtual classroom. Step on inside and, here, I wanted to clarify something. A student had asked me, Mr. Robinson, what do you mean by all math-based of course? What are you talking about? I'm saying, because he's like, it's a math channel, and I said, no. A brand new and exciting video, it's all math-based excitement. Of course. I mean, it's going to be math, so I'll spice it up however I need to with whatever I do, whether it's my canter and delivery, or maybe it's quite boring. There are sometimes when I'm clearly bored with it myself, but all math-based excitement. All math-based excitement. That's all I mean. Anyway, hey guys, dive in. Chapter 9 review in the Big Ideas Math Integrated Math 2 textbook, covering 9.1 to 9.6 on Pythagorean theorem, special right triangles, similar right triangles. I forgot about those, actually, a little bit. Trig functions, tangent, sine and cosine. I'll probably say sine, cosine, tangent a lot. And then solving right triangles in general, finding angles, measures of angles in right triangles, and all that good jazz. I think 23 problems to do, and they have some example ones beforehand. Check out the description section down below if you'd like to find PDFs of the following things. I don't think any graphs are involved. You might need your calculator. That's almost for sure. For sure. And download something if you want to, but follow along with me as we guide into the Chapter 9 review. Right after this, I plan on recording the Chapter 9 test and cumulative assessment video, so just one after the other in succession if you want a good abundance of problems. Let's see what they have in store for us, however, though. 9.1 in the Pythagorean theorem, they're trying to show you how to find the value of x using the theorem a squared plus b squared equals c squared. And yes, that is the theorem. 15 and 20 represent legs of the triangle. X, the unknown, is the hypotenuse, which should always represent the C. 15 squared is 225. 20 squared is 400. They add to 625. Square root of that is 25. Now, it is an integer value. These are all integers. That makes this a Pythagorean triple. It is specifically of the 3, 4, 5 triangle, similar triangle Pythagorean triple, as in 15 is 5 times that of 3, 20 is 5 times that of 4, and 25 is 5 times that of 5. 3, 4, 5 is one of the Pythagorean triples, which you might want to be familiar with. The other ones are the 5, 12, 13, 8, 15, 17, and 7, 24, 25. They can help you save some time. There are going to be other problems, such as ones that we do, that it's possible that they're not Pythagorean triples, but instead with radicals where we do have to simplify said radicals. So let's get ready for those. Let's start with number 1. We have 6, 10, and this unknown x. This is not a Pythagorean triple, not one of those that, it's not a 3, 4, 5 or anything like that. 6 squared plus 10 squared equals x squared. X is the hypotenuse, so 36 plus 100, you can see, is not a perfect square value because, I take the square root and I don't get an integer out from it. But is there something we can simplify this with? You can definitely divide by 4. I can say that this is the square root of 4 times the square root of, unfortunately, I don't know the other, 34. So this is 2 times the square root of 34, not a Pythagorean triple. If they ever ask whether it is, that one is not, because it is not an integer. And that's kind of how we build off of that. Number 2, this time the x is not the hypotenuse, but one of the legs. And also not a Pythagorean triple. Well, I take it back. This is a Pythagorean triple. So I'll tell you right now the answer is 12, knowing that it's part of the 3, 4, 5 special right triangle unit. But if you're like, how'd you do that? 5 times 4 is 20, 4 times 4 is 16, 3 times 4 is 12, knowing it's from that Pythagorean triple set. This will be, but let's continue on with the math. Now, we saw these two numbers before, or excuse me, we saw not 16 squared, but we saw 15 squared, but it was on the side that was adding with the 400. This time I take away from 400 and I get 144. Take the square root of both sides, you get x equals 12. 12 being not only the number that I predicted out of the Pythagorean triple, but it being an integer value with the other two being integers means that, yes, this thing is indeed a Pythagorean triple. Not just 12, but 12, 16, and 20 together represent a Pythagorean triple. And then number 3, x is also a leg here. Don't confuse a slanted part for hypotenuse. As long as it is making the right angle as one of the sides, it is a leg. This is not a Pythagorean triple, by the way. The hypotenuse is always opposite the right angle. So there's that in case you weren't certain. So this will be 120. Surely can divide by one of the perfect squares, if not four, if not just four, then perhaps something bigger. Let's see, 9, no. 16? Not 16, 25, no, 49, no, 64. No, just 4. So divide it by, or factor of 4 out, square root of 4, you get 2. And then the other one is 29, 30. Why did I have so much trouble with that? 4 times 30. So 2 root 30 is that value when simplified. That is not a Pythagorean triple. All right, that's numbers 1 through 3. Also in the section, although not a part of the example thing that they gave, verify the segment lengths, form a triangle, and is it acute, right, or obtuse? Here we use a Pythagorean theorem setup to show whether its converse holds up. First of all, with the numbers 6, 8, and 9, we need to first verify that 6 plus 8 is greater than 9. Is that so? Yes, it is indeed, because 14 is greater than 9. This has to be true for all triangles. The sum of the two smaller sides has to be greater than the third longest side. Now let's see how 6 squared plus 8 squared compares to 9 squared. 36 plus 64, and here's 81 on this side. That's a question mark, sorry. That's 100. 100 is greater than 81. Now, if these equaled each other, then you'd be looking at a right triangle. In a right triangle, a squared plus b squared equals c squared, and if a squared plus b squared equals c squared in a triangle, that means it's a right triangle. However, a squared plus b squared here is greater than c squared. That is indicative of an acute triangle. Acute triangles do that. Notice that I had to do the smaller sides on this side compared to the longest side there. Otherwise, you're always just going to be acute because you'll have one of the longest sides there. So this is where it comes into question on number 5. And I feel like they're growing in length on all of these, but let's take a look. We got 10, 2 root 2, and 6 root 3. I have every reason in the world to believe that 2 root 2 is less than 6 root 3 because both of them are smaller numbers. But how does 2 root 2 compare to 10? How does 10 compare to 6 root 3? These are the questions. If I go to the calculator just to kind of, and there are other ways I could do this, I'll show you them. But if I go to the calculator here, I can do, you know what 10 is. Here's 2 times the square root of 2. Oh, that is not right. Here's 2 times the square root of 2. All right, well, clearly even less than 10. So I guess they don't just go up in rank. That's a smaller number. It's one of the legs. And 6 times the square root of 3, 10.39, very close to 10, but more than 10. So that's the biggest of the 3 numbers. Now, the first thing they want you to do is just verify this works in a triangle. Does 10 plus 2 root 2, is this greater than 6 root 3? Let me kind of question mark this thing. Let me put it in blue. So, curious, is it greater than? Well, you just kind of saw what these numbers were. There's no real way to simplify it other than to round values. So this is around 12.8. Sorry, let's use blue. The other one was 2.82, right? So 10 plus 2.8 is around 12.8, and that is indeed greater than, this checks off by the way, greater than 6 root 3 is 10.4-ish. So yes, that does work as a triangle. In and of itself, we compared the two smaller sizes, the third biggest. And I think, yeah, I don't know, but there's that. So anyway, 10 and 2 root 2 are the smaller numbers. 6 root 3 is the biggest one. So we check and see how 10 squared plus 2 root 2 squared compares to 6 root 3 squared. Let me try that again. Now, there's good practice within here, knowing how to square things with radicals. 10 squared is 100. 2 root 2 squared, you can use the calculator, but 2 squared is 4, root 2 squared is 2, and 4 times 2 is 8. So we have 100 plus 8, and 6 squared is 36, root 3 squared is 3. 36 times 3 is 108. Now, this is where I said is another way you can do the test. Square the numbers to begin with. Square the numbers to begin with to find out which one's the biggest among them. 6 root 3 squared is more than 10 squared. Therefore, 6 root 3 is the bigger number. Seeing it in this light kind of helps show that. But 100 plus 8 is 108. And 108 is the same as 108. So, you know what? This is a right triangle. They are equal in value, where this would be the hypotenuse of this. 10 squared plus 2 root 2 squared equals 6 root 3 squared. So there's the test, there's the check, and it all pans out. Although I did have to verify this was a triangle, so I guess you found out the values and compared them properly there as well. So nothing really hurt, but we worked on it. And then number 6, 13, 18, and 3 root 55. I can only imagine that 3 root 55 is the biggest one. This one I'll validate in another way, just straight up. The square root of 49 is 7. 3 times 7 is 21. That alone is already more than 18. So 3 root 55 must be more than even 21. Therefore, it's more than 18. So the first thing, we still need to verify this works in a triangle, though. It will. I don't think there's a question as to whether they ever will. 13 plus 18 is 31. And 3 root 55 is 22.2-ish. 31 is greater than 22.2. So this is a triangle, all right, but what kind is it? Kind of hoping for an obtuse triangle this time. Let's see. Let's do 13 squared plus 18 squared and see how this compares to 3 root 55 squared. This is 169. This is 324. And 9 times 55, 495. This will push pretty close, actually. Oh, this will push very close. Is that 491? I think that's 491. Let's double check that. 160. I don't want to be wrong. 169 plus 324. 493. I don't know where I got that. But, I don't know how I got that. So 493. Not quite 495. Very close. I did not expect it to be that close. C squared is greater than a squared plus b squared. Or a squared plus b squared is less than c squared. This is an obtuse triangle. Obtuse triangles do that one. So we slowed a little bit to a crawl in those last 3 problems, but that's what we're testing on those when we go ahead and give it a look. All right, let's keep moving forward. Let's look at section 9.2. Let's look at what the example asks of us before we move into the problem sets. 9.2, we're going to find the value of x, write your answer in simplest form. This is with the 30, 60, 90 triangle and the 45, 45, 90 triangle. Here's the one that they pinpoint right here. Finding the value of x in a 45, 45, 90, you have a 1-to-1 to root 2 ratio relationship in these triangles. I might draw these out for you later. What I mean by that is that these lengths are equal to each other, and this length is the square root of 2 times larger. So they're going to take 10 and multiply by root 2, and you get, hey, 10 root 2. And that's in a 45, 45, 90 triangle. Whereas the 30, 60, 90 triangle, if I draw it kind of this way as well. So I'm using my mouse to write these ones. My stylus won't fit over here. This is a 1-to-2 to root 3 ratio relationship. I'll keep pointing to these as far as what they mean. But it's a matter of multiplying versus dividing some values to get the unknowns that you're looking for. On number 7, we have this 6, 6x and a 45, 40. Oh, so, excuse me. We have 6, 6, and the unknown x. Now, you could solve this using Pythagorean theorem, no doubt. But because these are congruent to each other, it's an isosceles right triangle, which will only be possible if these were both 45-degree angles. So this is a 45, 45, 90 triangle, which means they share that 1-to-1 to root 2 ratio relationship, which means x, just like in the example problem, is root 2 times larger than 6. X equals 6 times root 2, which of course is 6 root 2. And if I use Pythagorean theorem, I'd be getting the same thing. Can you use Pythagorean theorem in all of them? No. Once we start looking at a problem like this one, it kind of is you're unable to. On number 8, we have a 30, 60, 90 triangle. If one of them's 30, we know the other one's kind of got to be 60 with it. So 30, 60, 90. I'd like to happily put in the 60. Here's the 14, here's x. In this triangle here, we know the hypotenuse. Now, if you saw how I drew this, kind of unconventionally upside down, you can see that the hypotenuse is twice as big as the shortest leg. So we can divide by 2, not square root of 2, but by 2. Make it twice as small, you will get x. Seems like some of the easier problems that they have. You probably want to check out the problem set that we do in the actual, in the actual section to see what other ones we have. Maybe 9 will pose a different kind of challenge. Not really. This is very interesting, these 3 problems. Maybe there are 3 more on the other side, but somehow I doubt that. Number 9. Yeah, we're never multiplying by root 3 or rationalizing a denominator. Yes, definitely check out more in that section stuff if the Chapter 9 test and cumulative assessment doesn't provide you with that more. But here's 8 root 3. Sorry that's blue, but here's 60 and 30. This is opposite the 30, which is the 1, if you will. The x, this unknown, is the hypotenuse, which is twice as long as this. Very, very interesting set of problems, choice of problems, to not diversify themselves so much from not only the example, but yeah, not to simplify any radicals, not to rationalize any denominators, never to deal with the long leg, going from the hypotenuse to the long leg. Very interesting, but we do get 16 root 3 as the answer. You still got to know how to do it. It's just this doesn't cover everything under the sun. I do encourage you to find more problems of the sort, either from the 9.2 section or check out and see if this Chapter 9 test and cumulative assessment provides you with any more kinds of problems like this, even if it's one more. All right. Yeah, because we move forward. Let's get section 9.3 on similar right triangles. Now, they are going to heavily hit. Oh, they don't do it in these problems, so I might not either. But they, oh, no, yes, they do, right here. They hit on the geometric mean of these values, and I'll bring about that. They also do right triangle redrawings, which is a great way to do these if need be. A lot of ways to talk about this. I spent a long time talking about it. Again, if you want to hear more about this, check out the 9.3 section. Although I kind of I don't chastise how the book does it. I'll chastise how you how you will use misinformation within the book or not learn what you're doing if you don't set up proportions as well. All right, let's look at their example. We have basically a right triangle here with an altitude drawn on the inside of it. And what it does is it creates 3 similar triangles. This triangle ABC is similar to triangle BDC is similar to triangle ADB. That's because if you, and I said them differently, but if you redraw all of them to face the same direction, you have a hypotenuse on the bottom, a short leg on the left side, and a long leg on the right side like that. And they actually are all similar using angle-angle. Similarity, something from last chapter. Point being, corresponding side lengths are proportional to each other. And you can see right here, you could set up such a proportion for these ones, like 2 over 4 equals 4 over x. 2 over 4 equals 4 over x. And if you do so, you cross multiply, you can do 4 times 4. That's 4 squared. 2 times x, well, that's 2 times x, right? You can cross multiply and get that setup. How'd they get to the setup? There's an idea of geometric mean, and they have a few of them. That this guy here, this altitude is the geometric mean of these 2 numbers, which means you can set up this exact proportion, or it means that this squared equals this times that. It's kind of weird. I'm not going to reteach it all. This guy represents the geometric mean of this number and this number. Not that we have this situation, but this squared equals this times the whole thing. And then this squared equals this times the whole thing. Once again, you can see why I'm kind of anti that. So I probably won't talk about those unless I set up a proportion first. Anyway, they end up solving for x. They get 8 of that. That's the value of x. Let's look at number 10. Given number 10, it's pretty much the same setup as the last one. Here's how I'm going to call it out, though. I'm going to set up a proportion. We have a small triangle, a medium triangle, and a big triangle. In the big triangle, I only have the hypotenuse of 6 plus x. I don't have a long leg or short leg, and I don't have any corresponding parts in the small triangle's hypotenuse or the medium triangle's hypotenuse. So ignore the big triangle completely. Let's look at the small triangle where you have the short leg and the long leg. In the medium triangle, you have the short leg and the long leg. These parts correspond without making a redrawing. I can correspond parts. I can do the short leg of the smallest to the short leg of the medium triangle, as the long leg of the smallest to the long leg of the medium triangle. There's a setup. When I cross multiply, I get 9 squared equals 6 times x. Now, I bring up 9 squared instead of saying 81 to make mention of this squared equals this times this. That's another way you can write that part if you are well aware on how the geometric means work. So 81 equals 6x. Divide both sides by 6. You get x is 81 over 6. And that reduces to, that's an x. That reduces to, I did it again. 6. 6 has an x in it. Maybe that's why I was thinking that. That reduces to 27 over 2, or 13.5. And I didn't know that until I reduced it to 27 over 2. And that's the answer. Number 11. Once again, a very similar-esque setup, only this time x represents that middle. X is the geometric mean of 6 and 4, as if to say 6 over x equals x over 4. That is the long leg of the medium over the long leg of the small equals the short leg of the medium over the short leg of the small. So there's my setup. Cross multiply, I get x squared equals 6 times 4. That's a times, by the way. That's not a point. Let's just do that. So x squared is 24, and you can take the square root. It actually would have been better to just use this as it was. Take the square root of both sides, you get, once again, root 4 times root 6, or 2 root 6. Let's leave it exact, as we should. And then number 12, this is a different kind of setup. This is one of the other parts. This probably uses the big triangle this time. So allow me to use how I would generally set this up. I need to know x. X represents the hypotenuse. It's the hypotenuse of the big triangle. Do I have the hypotenuse of another triangle? Yes, the medium triangle. So I could already set up an x over 20, hypotenuse of big over hypotenuse of medium. Let's go big over medium again with 2 corresponding parts. What do I know in the big triangle? 20. 20 is the long leg of the big triangle. Do I have the long leg of the medium triangle? Yes, 16. So 20 over 16. 20 over 16. When you cross multiply here, you get 20 squared equals 16 times x. And I only write that again to remind you that this squared equals this times this. 20 is the geometric mean of 16 and x. Maybe you know that part, maybe you don't. That's why I set up proportions beforehand. Whoa, I did not think I chose red. 400 equals 16x. Divide by 16, you get x equals, I think that's 25. Yep. All right, that's 9.3 in a nutshell. Let's move to 9.4. This is where we start hitting trig, specifically tangent. Find tangent of m and tangent of n. Write each answer as a fraction and as a decimal round to 4 decimal places. This is where the calculator will definitely be used if I got to do some rounding I'm not aware of. So we have this right triangle here, 6, 8, 10, which is also a 3, 4, 5 right triangle, by the way. You take the tangent of angle m. Tangent is opposite over adjacent. That's something to remember in SOHCAHTOA. SOHCAHTOA. This is not something the book ever spells out, but I will. Tangent is opposite over adjacent. Here's angle m. Opposite of m is 6. Adjacent to m is 8. The adjacent leg. 6 over 8 reduces to 3/4. 3/4 is 0.75. To 4 decimal places, 0.7500. Tangent of angle n. Tangent of angle n is opposite over adjacent. Opposite the n is 8. The adjacent leg is 6. And 8 over 6 reduces to 4/3. 4/3 is 1.3333 to 4 decimal places. So let's go ahead and try this for ourselves. Let's do number 13, where we have this triangle, tangent of j and tangent of L. Those are angle measures, or at least angle locations and descriptors. I'll just bring this over so you can see what we're talking about. Tangent of angle J. Tangent of angle J is, here's J, opposite over adjacent is 11 over 60. Now that can't reduce, and I also don't know its decimal approximation, so I will go to the calculator for that. You can't see it, but 11 divided by 60, I'm too lazy to show it, 0.1833. There are 3's repeating after that, 0.1833. So here's the exact reduced fraction. Here is the decimal to 4 places. Tangent of angle L. Angle L's opposite is 60. Its adjacent is 11. So you really do just flip it in these cases here. 60 over 11 also cannot reduce, but let's see what that is. Well, it's going to be 5 and 5/11ths. And 5/11ths, I think, is point... I don't remember. I don't remember how the 11ths work. Oh, 0.454545, I think. So let's see. 60 over 11. So I think it's 5.454545. 60 over 11. 5.454. So how does that round? 5.4545. All right. This kind of math. Okay. Number 14. A word problem. The angle, this is all tangent, by the way, on these. The angle between the bottom of a fence and the top of a fence is 75 degrees. Top of a fence and top of a tree, 75 degrees. The tree is 4 feet from the fence. How tall is the tree? Round your answer to the nearest foot. If you can't see the diagram, well, here's the thing. Sometimes you got to draw your own. So I'm just going to redraw the triangle that they represented. But if you need to understand the diagram. Let's say it again. They have that. Okay. So here, what do they say again? Here's the tree. Here's the bottom of the fence. The angle from between the bottom of a fence and the top of a tree is 75 degrees. That's an angle of elevation upward. The tree is 4 feet from the fence. That's the closest distance. The one at the bottom of the tree, bottom of the fence. How tall is the tree? Okay, so that's what we're setting up. Tangent of 75 degrees is what I want to use here. I can get the opposite over adjacent setup as such. We multiply both sides by 4, and we get 4 times the tangent of 75 degrees. That's an exact answer, I guess in feet. But let's go ahead and round that, and then let's put feet to that. They said round your answer to the nearest foot. Must be either close to a foot, or they just want to put it that way. Yeah, pretty close. 14.928, around 15 feet. Around 15 feet is that tree. They never said how tall the fence was. Boo-hiss. Okay. Let's move to section 9.5, which is a continuation of trig stuff, basically. So is 9.6 with added wrinkle. But 9.5 is sine and cosine. Sine, you saw SOHCAHTOA. Let me bring that over here. SOHCAHTOA. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse of any angles. Now we're going to highlight these guys here, sine and cosine. You'll see them also place that here. We want to find the sine of angle A and B, cosine of angle A and B. Write each answer as a fraction in decimal. Sine of angle A, here's angle A. We're going to do opposite over hypotenuse. Opposite over hypotenuse. That's opposite over hypotenuse. 30 over 34 is 15 17ths, 0.8824. Sine of angle B, here's B. Here's its opposite over hypotenuse. 16 over 34 reduces to 8 17ths. By the way, this is the 8, 15, 17 Pythagorean triple, which is 0.4706. Now, cosine's adjacent over hypotenuse. The cosine of angle A is the adjacent leg 16 over the hypotenuse 34. 8 17ths. Hey, we've seen that before. It's this guy here. And then cosine of angle B is the adjacent over hypotenuse. The adjacent is 30 to the B. Hypotenuse is 34. Hey, we've seen that before. That is the same as this guy here. There's a link. And that is not going to be any different for any other problem. The sine of one angle is the cosine of the other angle, the complement in a right triangle. So much so that that's the case, I'm going to use that pattern in this problem. I did it in the problem set that we actually played with in the section. I'm going to do that here. They say find the sine of x, sine of z, cosine of x, and cosine of z in this triangle that you see on number 15. So if I take the sine of x, guess what? That's also the same as the cosine of z. Want to know why? Because sine of x is opposite over hypotenuse. Cosine of z is adjacent over hypotenuse. They're both 7 over root 149. No matter what we do there. Now, they did say round your answer, write each answer as a fraction and as a decimal rounded to 4 decimal places. The first thing I actually want to do is rationalize the denominator. Whenever they say fraction, clearly they mean simplified. Does 149 simplify? Not with 7. Does root 149 simplify? I don't think so, otherwise they would have already done it. So I'm going to leave it like that, but rounded to 4 decimal places, I'm just going to type 7 over root 149. That's faster. Simplified doesn't always mean less. Sometimes it just means simplified. And that's 0.5735 if you round it appropriately. 5735. It says 346. So 0.5735 is both the sine of x and the cosine of z. Now the sine of z is going to be the same as the cosine of x. The opposite over hypotenuse of this guy is the same as the adjacent over hypotenuse of this guy. 10 over root 149. Now again, simplified, you rationalize the denominator, multiply both top and bottom by root 149, and you get that. Not clean looking, but it is a value. Rounded here, not going to be much bigger than the other guy. 10 over root 149. 0.8192. 0.8192. Okay, that's number 15. Number 16, 17, and 18. Find the value of each variable using sine and cosine. Round your answers to the nearest tenth. Keep SOHCAHTOA in mind when it comes to which one you want to use here. Well, actually, we're going to use both. But keep SOHCAHTOA in mind when you use which one. Here's t, here's s, here's 23 degrees and 34 units in length. This is the hypotenuse. Relative to the 23-degree angle, t is opposite, divided by the hypotenuse. I can use sine for that scenario. The sine of 23 degrees equals t over 34. If I multiply both sides by 34, I get t equals 34 times the sine of 23. That's exact. Rounded to nearest tenth, 1 decimal place. Okay, 34. By the way, make sure you're in degrees. Let me show you this one. Make sure you're in degrees on this guy here. I should have been beforehand, by the way. 34 times sine of 23. I'm getting 13.28. They said 13.3. They said round to the nearest tenth. So there is when I would use sine, why I would use sine. Let's go back and let's try to find s. S is adjacent to the 23. That's supposed to be green. S is adjacent to the 23. The hypotenuse is 34. That's where I can use cosine. Cosine of 23 degrees is s. That's not a 5. S over 34. So s is 34 times the cosine of 23 degrees. It'll be a different number. Cosine uses a different ratio relationship. And if you want to hear me explain more about it, of course, I do it in section 9.5. I talk a lot about this trig function stuff also in section 9.4. 31.3. 31.3. That was 13.3. This is 31.3. And yes, that is a decimal right there. So there's exact, there's approximate. We got it. That's number 16. We move forward and do the same thing on number 17. Really not much different whatsoever. This time I won't draw it. Just take a look at the diagram over there. See if you can identify when we should use sine versus cosine. Note that 5 is the hypotenuse. And oh, of course, they have a 5 with an s. They cannot help themselves. So, opposite the 36 is s. Hypotenuse is 5. Let's see how good I can make this look. The sine of 36 degrees equals s over 5. Okay, I think those look different enough. Multiply both sides by 5. You get s is 5 times the sine of 36 degrees. What's 5 times the sine of 36? Oh, it is 2.9, about 2.9-ish to the nearest tenth. Let's check out how cosine fits into all this, because I got to use that to find r. R over 5. Multiply both sides by 5. You get r is 5 times the cosine of 36 degrees, which is about 4.04, so 4.0. 4.0 units in length there. That's number 17. And number 18. So they're not changing hat on how they do any of these, which is a bit unfortunate. I wish that they had one where they had one of the other lengths, but I understand if we can't use sine to find one of them. I kind of get it. I think we'll save it for section 9.6. So number 18, the 70-degree angle. Opposite it is the v, so sine of 70 degrees is v over 10. Multiply both sides by 10, you get v is 10 times the sine of 70. And I think you can imagine that w is 10 times the cosine of 70. These aren't really changing what we're doing here as far as, adjacent over hypotenuse. I want to kind of slightly speed that one up. Just if you start catching on to a pattern, this does apply if you recognize where the pattern works. We are going to see a break in that pattern, I'm sure, at some point in section 9.6 where we have to divide by the sine or cosine of something, but it's because we have the hypotenuse that this is so. This one is 9.4, and the other guy is 3.4, approximately. There we go. It's number 18. All right, numbers 19 and 20. Number 19, write sine of 72 degrees in terms of cosine. Well, this goes back to kind of what I was talking about with regard to where this applies. So sine of 72 is what you're talking about when you have a 72-degree angle in a right triangle. Now, you get opposite over hypotenuse, right? This x over y here. How do I get cosine of something to get that x over y? What I got to do is find the complementary angle right here. I have to find this one because cosine would give me adjacent over hypotenuse. So here I got to do 90 minus 72. That is going to be 18 degrees. Sine of 72 is cosine of 90 minus 72, which gives you 18. That's how you do any of those ones. You should get the same answer in both. Your graphing calculator, or your calculator, can confirm that sine of 72 and cosine of 18 give you the same value. It doesn't matter what the ratio is. It just says write it in terms of the other. Yes, those are the same ratio. Whatever that x over y is what you get. There's only one problem of that type, it looks like, so I'm going to move forward. Number 20, given that sine of theta equals 24/25, find cosine of theta and tangent of theta. This is one where the book would do it differently than I would. It's not unappreciated on how the book does it. It's just longer. You have to deal with kind of fractions in a deeper way. They hit hard on the fact, this Pythagorean identity, that the sine squared of theta plus the cosine squared of theta equals 1, not a formula which you should dismiss. This is absolutely one that when you hit IM2, pre-calc, things of that nature, that you got to use this. Yeah, be ready. And they also hit on the fact that tangent of theta is sine over theta over cosine of theta. Using these things together, you can, of course, indeed get the answer. If you take a picture of this thing and use photo math or something like that, I'm sure you can find their work. I'm going to do this alternatively, and it's just as fun, just as easy, just as efficient. It doesn't use these, but there you go. But I do make a drawing. Imagine in a right triangle you have an angle theta here, and sine of that is 24/25. If I want to find cosine and tangent of theta, I need the adjacent leg to this theta. Cosine is adjacent over hypotenuse, tangent's opposite over adjacent. So I just have to find x. So they use a Pythagorean triple here. I will use Pythagorean theorem, sort of. X squared plus 24 squared is 25 squared would be your setup to solve for x. But guess what? X equals 7. How do I know that? Because this is a 7, 24, 25 Pythagorean triple. Again, it helps to know them. But x is 7. Therefore, I can use that. So the cosine of theta is 7 over 25. Can't be reduced. That's exact. And the tangent of theta is 24 over 7. Also can't be reduced. That's an exact. This is a lot less work as an overall. I didn't have to really use Pythagorean theorem. You can go ahead and continue to see how it is. But this is a review of things that are expected that you should have heard once before from me. Or from your teacher, or wherever. See if you can get those answers using alternative methods. Finally, section 9.6. Solving right triangles. We have 3 questions to do, but first let's take a look at their example that they have. They have 2 of the legs, no known hypotenuse. We can solve that using Pythagorean theorem. It is not a Pythagorean triple, and they round their value of 22.5 once they use their Pythagorean theorem setup. They round it. Try and not use the rounded value to get other answers, though. Try and use exact answers that you know, like 12 and 19. So let's find the measure of one of these angles, B or A. They find B by taking what's called the inverse tangent of 12 over 19. See, the tangent of B is 12 over 19. The answer is a ratio. If you want to find the angle measure, you take the inverse tangent of the ratio, 12 over 19, and you'll get the angle. Just make sure you're in degrees in your calculator. I'll make sure to show you this when we do a problem. How do I find A? If I know that B is 32.3, then A is 90 minus 32.3, and you'll get 57.7 degrees. So that is their problem that they had as an example. Let's try one for ourselves. Let's go to number 21. We have this triangle here. I'm going to copy and paste it. Too lazy to draw it out. Don't want to make it look bad. So we got this blurry mess instead. So on this guy here, we know 15 and 10. Let's find the length of BC using Pythagorean theorem. Not a Pythagorean triple, by the way. 10 squared plus BC squared is 15 squared. Whoa. So BC squared is 125 when you subtract that, and BC is the square root of 125. Now, as an exact answer, that would be 5 root 25 when 5 root 5 when simplified. However, they don't really care about that. They're going to care more about the rounded value. Square root of 125, 11.18, so around 11.2, and that is this value here. Okay, I found one of the values. To solve a triangle, I didn't mention this. To solve a triangle means to find all the missing values in the triangle. We find all 3 legs, or all 3 sides, and all 3 angles. We know 2 of the sides. We know the right angle. Let's find one of these angles here. Let's find, say, angle B. Now, try and avoid using 11.2 because it's rounded, and I don't want to write that or that over and over. So let's use the 10 and the 15. 10 is opposite the B. 15 is the hypotenuse of the triangle. So I should use sine to find this. So here will be my setup. If I take the sine of b, I get 10 over 15. Now I'm leaving space on purpose for this particular part of this problem. I will take the inverse sine of both sides in order to solve for b. That is the way that this works. Now they didn't write this out as far as this cancels that part out, and you're left with just the measure of angle b now. Measure of angle b equals, and the inverse sine of, see this is what they write, inverse sine of 10 over 15 is here. Could I reduce 10/15? Sure. Do I want to avoid making any mistakes? Yeah. I'm just going to go to the calculator anyway and hit inverse sine. Inverse sine is above the sine button right there in yellow for me. It is in most calculators. I got to hit the second button to shift it up, and I do 10 over 15 here. This will give me an angle measure. The angle measure is 41.8 degrees, and that is the measure of angle B. So 41.8 degrees is the measure of said angle right there. Measure of angle A will be 90 minus that. I know that 41.8 is rounded, but it won't change the rounding of A if I do an addition or a subtraction off of a single rounding. So 90 minus 41.8 is about 41.8, I should say, is about 48.2 degrees. And that's A, and this is a solved triangle. One of three triangles to solve. So that's the first one. In the second one, this time we have, get set up. This time we have in a right triangle, we have one of the sides known and one of the angles known. So this setup might look a little bit different, all depending on what you do. I can't really use Pythagorean theorem this time anymore. A lot of trig might get involved. I need to find out the length of NL and the length of LM. And then I need to find this other angle. I'll save the angle for last, make the easiest part last. Let's start with ML. It's opposite this 37 when we know the adjacent to 37 is 6. That means we got to use tangent. The tangent of 37 degrees is LM. Sorry, I want to go alphabetical. LM over 6. So LM is 6 times the tangent of 37 degrees. That's exact. I'll go to the calculator, 6 times tangent of 37. And I get 4.5 about 4.5. So that's this guy. You could use Pythagorean theorem on these two to find the third, but keep in mind this is rounded. I don't want to use a rounded answer. Let's just do trig again to find this one. And it's probably the first time in the review that we'll do something slightly different. We're going to use cosine. Cosine of 37 is 6 over this unknown. Cosine of 37. The difference is, to solve for this ln, I don't multiply both sides by 6. I don't even divide both sides by 6. I multiply both sides by ln and divide both sides by cosine of 37. This is where these guys kind of switch places. So there's that answer. You'll know something screwed up if you got an answer less than 6 or less than 4.5. This should be the biggest side on here. 6 divided by cosine of 37. I am getting 7.5-ish. And that is that length. Which means 6 squared plus 4.5 squared should be about 7.5 squared. Yes, they're rounded. This last one here, measure of angle L, is going to be 90 minus 37. So that's the easiest part, and it's exact as well. This is 53 degrees. So 53. And the triangle is solved. Lastly, the last problem in this review, we have number 23, which is actually a lot like 21. In all honesty, there's really no difference in what I want to do to find some of the values. Let's see how the values change, though. Let's copy and paste this guy and fill out parts. Let's find the length of xy first using Pythagorean theorem like we did last time. So xy squared equals 18. Oh, excuse me. Xy squared plus 18 squared equals 25 squared. Also not a Pythagorean triple that I'm aware of. Xy squared, maybe it is, plus 324 equals 625. Xy squared equals, that's 301. I've seen that number before. Only thing I seem to remember was it wasn't a... You couldn't simplify it, but oh well. Square root of 301. 17.3, about 17.3. So there's the length of xy. Okay, let's find angles x and z. What did I use before? Inverse sine. This time let's do an inverse cosine. Let's find the measure of angle z by taking inverse cosine of 18 over 25. If you understand now how those things are set up, the cosine of z equals 18 over 25. Therefore, measure of angle z equals inverse cosine of 18 over 25. So I go to the calculator, inverse cosine. That should be above cosine, by the way. 18 over 25. The degree measure here is 43.94, so 43.9 degrees. Notice how I kind of tried to use the exact values as often as I could, 43.9. And measure of angle x. Measure of angle x should be 90 minus that. Measure of angle x equals 90 minus 43.9, which is about 46, 46.1. 46.1 degrees. I only hope I calculated that right. There's a possibility that I miscalculated. But that solves the triangle. That is what we're looking for. That is the last problem there. And that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching the Chapter 9 review. Coming up next, immediately, I'm going to be recording the Chapter 9 test and cumulative assessment video. And at some point, I'm sure my colleague's going to make another Are You Ready Chapter 9 review. Maybe it gets better questions than these and more diversified. And we'll see what we do there. Thank you so much for watching, guys. Take care. I will see you in the next one.